It is 3:28 a.m. Your pager's going off.
Oh, the absolute worst feeling in the world.
Right. Your Java microservice, the one that processes literally thousands of financial transactions a second, has just ground to a complete halt.
Let me guess, a massive garbage collector pause.
Exactly. A stop-the-world pause. You drag yourself to the monitor, and the telemetry just confirms it. The GC is frantically sweeping through the heap, trying to clean up millions of abandoned objects.
And you're just sitting there watching the latency spike.
Yeah. And in that moment, you're wishing you could just manage the memory yourself, right?
Yep.
Just keep the latency flat. But then you remember your university days.
The C++ segmentation faults.
The memory leaks.
Yeah.
And you realize you are totally trapped. You're caught between the unpredictable lag of a garbage collector and the catastrophic danger of manual memory management.
Which is really the defining struggle of modern back-end engineering. I mean, we want the absolute control of C, but we desperately need the safety net of Java or Python.
And since you, the senior back-end engineer listening to this, already know that's the exact promise of Rust, we are skipping the preamble today.
Yeah, you already know the why. You want memory safety without the GC overhead.
Right. And you've got your cargo toolchain set up. You understand the syntax from earlier chapters. So welcome to the deep dive. Today we are jumping straight into Chapter 3 of Rust for Backend Engineers.
The really fun stuff, ownership and move semantics.
The absolute core of the language.
Mm-hmm.
But consider this a friendly warning. Your existing intuition, those mental models you've relied on for years in Python and Java, they're about to be heavily challenged.
Oh, completely. Because it's a fundamental shift in philosophy. I mean, to get rid of the garbage collector, Rust has to solve memory leaks and dangling pointers at compile time.
At compile time, before the code even runs.
Exactly. And the way it does that is through this strict, uncompromising accountability. You know, in a garbage-collected language, variables sort of just, they share data.
Right, like a committee. If nobody is looking at the data anymore, the system just eventually comes along and cleans it up.
Yeah. But Rust fundamentally rejects that shared responsibility.
So if it rejects shared responsibility, I guess someone has to be held specifically accountable for every single piece of data, right?
That is the exact logic that leads us to the first golden rule of Rust. Every single piece of value, every chunk of data in memory, must have a single variable designated as its owner.
Just one.
Exactly one, not a shared committee of references, exactly one owner.
And if it's an exclusive ownership model, I mean, I'm assuming that means you can't have two variables owning the data simultaneously.
You absolutely cannot, and that's rule number 2. There can only be one owner at a time, period.
Okay.
If you decide to hand that data off to another variable, the original variable loses its claim completely. It's totally invalidated.
Which naturally leads to the ultimate consequence, right? If a specific variable is the sole owner of a piece of data, and that variable reaches the end of its block of code.
When it goes out of scope, yeah.
Right, when it goes out of scope, the data has no owner left. So it just has to be destroyed.
That's the third and final rule. When the owning variable goes out of scope, the compiler automatically inserts the code to clean up the memory. The value is, in Rust terms, dropped.
Dropped, okay.
Yeah. And these aren't just like best practices or nice design patterns. These 3 rules dictate the entire architecture of the compiler.
It really reminds me of a hyper-strict coat check at an exclusive club.
Oh, I like that analogy.
Yeah, so you walk in, you hand over your coat, and you get one ticket. And that single ticket is the only thing in the universe that matches your coat.
Mm-hmm. Just one owner.
Right. Only one person can hold that ticket at any given time.
Right.
And when the person holding that ticket leaves the club, when they go out of scope,
Yeah.
the coat leaves with them.
Exactly. You can't have 5 friends holding photocopies of the ticket expecting to get the same coat.
Because then the coat check attendant would just, well, they'd freak out.
Right. The system would crash. And that exclusivity is what gives Rust its power. But I have to admit, it's also what causes the most intense friction for newcomers.
Yeah, I can imagine. So let's look at the exact moment a Python or Java developer usually hits that brick wall. Let's talk about variable assignment.
Oh boy. The classic shock.
Right. So let's set the stage with Python. I create a list of strings called, let's say, names.
Simple enough.
Then on the very next line, I write also names equals names. Now, in my head, I've just created 2 separate reference variables.
Mm-hmm.
But they are both pointing to the exact same list object sitting on the heap. If I append a new name using also names, the original names variable sees the change too.
Yep, because the garbage collector just ticks up a little reference counter to 2 and moves on with its day.
Exactly. So the mechanism there is crucial. I'm copying the memory address, but I'm not touching the underlying data.
Both variables essentially feel like they own the list. Now let's translate that exact same operation to Rust.
Okay, let's do it.
You create a dynamically sized string. Let greeting equals string.from, hello. Then you assign it. Let also greeting equals greeting.
And if I try to write a third line of code that prints out that original greeting variable,
The program just refuses to compile.
refuses, it throws an error saying value used here after move, the variable is just dead.
Completely dead. And to understand why the compiler is yelling at you, we really have to look at the actual memory layout.
Right, because a Rust string isn't just a magical object.
No, not at all. It's composed of 3 specific pieces of data sitting on the stack. You have a pointer to the memory address on the heap, a capacity, and a length.
And the actual text, the word hello,
Yeah.
is sitting out on the heap.
Exactly.
Okay, so when I write let also greeting equals greeting, what is Rust physically doing with those 3 pieces of data on the stack?
It does a bitwise copy of those 3 stack values. It literally takes the pointer, the capacity, and the length, and copies them into the new variable, also greeting.
But wait, if it just copies the pointer, that means both greeting and also greeting now possess pointers looking at the exact same heap memory.
Yes. And that is exactly where the rules of ownership kick in.
Rule number 2, only one owner at a time.
Precisely. Because if Rust allowed both of those variables to remain valid, think about what would happen when they both reach the end of the function and go out of scope.
They would both trigger that third rule. Greeting would go out of scope and tell the system to free the heap memory.
And then also greeting would go out of scope a microsecond later.
And try to free the exact same heap memory.
Which is the infamous double free bug.
Oh, wow. Yeah, in C or C++1, telling the operating system's memory allocator to free an address that has already been freed that corrupts the allocator's internal state.
It's disastrous. It can crash your program instantly, or worse, it can allow an attacker to execute arbitrary code. It's literally one of the most critical security vulnerabilities in software engineering.
So Rust just prevents it from ever happening by invalidating the first variable the moment the assignment happens.
Yes. The data hasn't vanished, the ownership has just moved. That's why it's called move semantics.
Okay, I want to refine my old mental models here. In Java, assignment is like hiring multiple security guards and handcuffing all of them to the same briefcase full of cash.
That's a chaotic visual, but yes, any of them can access it.
Right. But in Rust, it's like there's only one pair of handcuffs in existence. If you take the briefcase and handcuff it to a new security guard, the old guard literally ceases to exist.
They evaporate.
Yeah, they just vanish.
Yeah.
You cannot ask them to open the briefcase anymore.
The old guard is struck from the compiler's registry because shifting the burden of memory safety entirely to compile time means the compiler must mathematically prove that a double free is impossible before the code even runs.
Wait, hold on.
Yeah.
If the old guard ceases to exist, what happens if I assign basic numbers? Like, if I write let x equals 42 and then let y equals x, does my integer just vanish? Because if x becomes invalid just because I assigned it to y, writing basic mathematical formulas would be an absolute nightmare.
Oh, totally. And the language designers anticipated that exact logistical nightmare. Not all data behaves this way.
Oh, thank God.
Yeah, the behavior we just discussed where ownership moves, that applies to data that manages resources on the heap. But for simple fixed-size data, Rust uses something called the copy trait.
The copy trait. Okay, so this is an exception to the move semantics. What kind of types fall under this category?
Primarily types that live entirely on the stack. So we're talking integers, floating point numbers, booleans, and characters.
Because their size is known at compile time.
Exactly. They don't need to allocate any memory on the heap at all.
So if there's no heap memory, there's no pointer to manage.
And therefore, no risk of a double free bug. That's precisely the underlying logic. When you assign let y equals x, where x is the integer 42, Rust just copies those few bytes on the stack.
And moving a few bytes within the CPU cache is trivially cheap, right? It's incredibly fast.
Super fast. So Rust allows both x and y to remain completely valid independent variables. Modifying y has no effect on x.
Okay, that makes sense. But what if I actually want that behavior for my heap data?
What do you mean?
Well, what if I have a massive string of JSON data and I genuinely need also greeting to be an exact independent duplicate of the text on the heap?
Ah, I see.
If Rust won't do it automatically to protect me from double freeze, how do I force it?
You force it by being explicit. You have to call the .clone method.
.clone.
Yeah. You would write let also greeting equals greeting.clone. And this tells Rust to go out to the heap, allocate a brand new block of memory, and copy the text byte by byte into the new space.
Which is a really expensive operation compared to just copying a stack pointer.
Very expensive.
So Rust is essentially forcing me to acknowledge the performance hit. Because in Python or Java, you might accidentally duplicate a massive array just because the runtime hides the memory allocation behind a simple equal sign.
Exactly. Rust demands that you type .clone so that the performance cost is painfully visible in the source code. Transparency is a core tenet of the language.
Oh, I see. So if you were reviewing a pull request.
And you see a .clone inside a tight loop, alarm bells should immediately ring.
Right, because you know an expensive heap allocation is happening over and over again.
Yep. And if you don't see it, you know the operation is either a cheap stack copy or a zero-cost move. The performance characteristics of your application are just laid bare.
Okay, I buy the strictness when I'm just renaming a variable or duplicating a string in the same block of code.
Sure.
But real backend systems aren't single blocks of code. We pass request objects through layers of middleware, validation functions, database controllers.
All over the place.
Right. So if handing off a variable destroys the original owner, how does data survive traveling through an application?
Oh, man. This is where the training wheels truly come off for Python and Java devs.
I can feel the friction already.
Yeah, because passing a variable into a function in Python or Java is incredibly casual. You just pass the reference in, the function reads it, and the caller keeps right on using the variable afterward.
Totally.
But in Rust, passing a variable by value into a function transfers ownership into the function's parameter.
Wait, let me trace the mechanics of this.
Go for it.
I create a string called message. I call a logging function called printMessage, and I pass message into it as an argument.
Okay.
Under the hood, a new stack frame is created for the function. The string's pointer, length, and capacity are copied into the function's parameter.
And because of that copy, the original variable in the caller's stack frame is invalidated. The function now owns the string.
And when the function finishes printing and hits its closing brace, its stack frame is popped off, the parameter goes out of scope,
Yeah.
the third rule kicks in, the memory is freed.
Yep.
I have literally destroyed my data just by trying to print it.
The data is gone. If you try to use message in your main code after calling the logger, the compiler absolutely stops you. Wow.
And this is the exact moment when most developers transitioning to Rust feel a profound sense of friction. I mean, the code looks completely standard, but the compiler fundamentally rejects the architecture of it.
Wait, hold on. I want to push back on the design logic here.
Please do.
If passing a string to a logger function consumes it, why didn't the designers just make the compiler automatically return the string at the end of every function?
That's a common question.
Because why put the boilerplate burden on me to manually return the string from the logger and reassign it back to myself just to keep using it?
Because an automatic return assumes that the function actually wants to give the data back.
What do you mean?
Well, imagine a function called saveToDatabase. Its entire purpose is to take your user object, serialize it, write it to disk, and then permanently close the connection.
Oh, I see. It is specifically designed to consume the data.
Right. If the compiler automatically returned ownership to the caller, it would create massive logical inconsistencies about the life cycle of that data. Rust makes zero assumptions about your architectural intent. It forces you to wire the routing explicitly.
Exactly.
So the language is demanding that I stop treating functions like casual observers of my data and start treating them like black holes.
Black holes is a great way to put it. If you throw a value in, it's not coming back unless the function specifically decides to spit it back out.
Yeah, it really demands intentionality. But obviously, manually returning every single string just to print it would make building large systems practically impossible.
Oh, it would be a nightmare.
So we're highlighting this friction to illustrate how strict ownership is. But experienced Rust developers aren't just constantly fighting the compiler all day.
No, definitely not. They'd never get anything done.
So how do they survive? How do we build that intuition so we aren't pulling our hair out every time we write a helper function?
By fundamentally changing the mental model before a single line of code is written. When you design a feature in Rust, you have to ask yourself 3 specific questions about every single piece of data.
Okay, what's the first one?
First, who is the definitive owner of this value at this exact moment?
So tracking the single point of accountability.
Exactly. Second, when I pass this data to a function, am I intentionally transferring ownership to let the function consume it, or am I just lending the data temporarily?
Lending the data. Okay, that sounds like a major hint at how we eventually solve the logging problem without destroying our strings.
It absolutely is. And the final question, is there any point in my architecture where I absolutely need the same data to be mutated in two different places at the exact same time?
Which, based on everything we've talked about with exclusive ownership, sounds like something the compiler is going to fight me on relentlessly.
Oh, it will fight you tooth and nail. Shifting your perspective means stopping treating variables as just convenient names pointing to data and starting to treat them as physical, legally responsible owners of a life cycle.
That is heavy.
It is. But once you internalize that a function call physically moves the data into a new stack frame, the compiler's verdict becomes totally predictable. You stop being surprised when it tells you the value is gone because you authorized the transfer.
It's a massive paradigm shift. But I think we've survived the initial shock of move semantics today.
I think so too.
We've mapped out the 3 golden rules: one exclusive owner, one owner at a time, and automatic dropping when they go out of scope.
Yep.
We've looked at the underlying memory mechanics of variable assignment, why the dot clone method makes performance costs visible, and the stark reality of how function calls consume ownership.
It really is a steep learning curve, but these mechanics are the absolute foundation. I mean, everything else in the language is built to operate safely within these constraints.
And I know we left a massive cliffhanger regarding that function call problem.
We did.
Rest assured, you don't actually have to destroy your strings just to log them. In Chapter 4, we'll dive into borrowing and references, which introduces the concept of lending data without transferring ownership.
That is the missing piece that makes all of this strictness actually practical for real-world development. Borrowing is where the language truly becomes elegant.
I'm looking forward to it. And once the interplay between ownership and borrowing clicks for you, the path really opens up. You'll be ready for advanced data modeling with structs and enums in Chapters 5 and 6.
And eventually the infamous concept of lifetimes in Chapter 9.
We will take that one step at a time. But before we wrap up this deep dive, I want to leave you with something to chew on regarding system design.
Let's hear it.
Rust's ownership model forces you to be hyper-aware of memory, absolutely. But consider the broader architectural implications. If passing direct memory references around an application is this heavily scrutinized and painful, maybe Rust is secretly pushing us away from shared state architectures altogether.
Oh, that's an interesting thought.
Right, because if it's this hard to have 5 functions looking at the same heap allocation, perhaps the language is nudging us to build decoupled, message-driven systems where we pass lightweight IDs instead of heavy memory addresses.
It makes you wonder.
Is the compiler just checking our memory safety? Or is it fundamentally trying to rewrite how we design back-end software? Think about it. See you next time.